Swayam Prabha. Digital India. Educated India.
Hello, welcome to the third week of our course on Introduction to Dynamical Models in Biology. This is the first module of this week. Here we will keep on discussing on the different dynamic aspects of system of ODEs. Remember, till now we have focused more on how the dependent variable changes or evolve with time and their steady states. In a ODE or in a system of ODE, you have multiple components. One is obviously the dependent variables, it may be one or more than one. And then you have the independent variable, for our case that is the time, and we measure everything else changing with respect to time. Apart from that, there is something else called parameters, which remain constant, which does not change with time. So, in this video, we will start discussing how these parameters can affect the dynamics of a system or the steady states of the system. So let us look into this issue. To understand the issue of effect of a parameter on the dynamics of a system, let us take a particular example. A simple ODE I have taken. dx dt is equal to m minus x square. So m is my parameter which remain constant. Does not change with time. So I want to see how the dynamics of this system or the system property represented by this ODE is getting affected by the value, numerical value of m. So let us see. Let us start the steady state analysis for this ODE. We know for steady state the derivative should be equal to 0, that is dx dt equal to 0, that means m minus x square is equal to 0. So let me separate out x and m. So I take x on the left hand side, I get x square equal to m. That means my steady state solution are x equal to plus minus root of m, square root of m. So that means I have two steady state value, x equal to plus minus square root of m. So let us take different values of m and see how the steady state changes. So when the first case, when m is greater than 0. If m is greater than 0, for example, value 4, 16 or something like that, x will have two steady state. One is plus square root of m, another one is obviously minus of square root of m. So if m equal to 16, then one steady state will be plus 4, the other will be minus 4. What if m equal to 0? When m equal to 0, then I have only one steady state, that is x equal to 0. What if m is less than 0? In that case, I get this one negative. The something under the square root is negative. That means I do not have any real solution here. Just look into these cases. Case 1, where m is greater than 0, I have two steady states. Where in the second case, where m equal to 0, I have only one steady state. When the third case, m is less than 0, I have no steady state. That means the number of possible steady state for this system represented by this particular ODE depends upon the parameter m. When the m is positive number, you have two steady state. When the m is a negative number, you have no steady state. When m equal to 0, you have just one steady state. I can represent it graphically. So what I have plotted here, x in the horizontal axis and dx dt in the vertical axis. And then I am plotting these ODE in this plane. So essentially I get these parabolas. Now when m is positive value, then I have this first parabola. And as you can see, this parabola is intersecting x at two positions. So this curve is intersecting x at two position. So at these two position, x is equal to 0. That means this is one steady state And this is also where x equal to 0, so this is another steady state. This is a very easy way to identify the steady state in dx dt versus x plane. So I have two steady state. I have considered m equal to 2, so that means this first steady state is square root of 2 and 0, and the other one is minus square root of 2 and 0. Now consider m equal to 0. Then this curve goes down and I get this one, this second plot. So this is for m equal to 0, and obviously this intersects the x-axis only at one point, and that is 0, 0. When m is negative, this curve goes down further. So this is the one for m equal to minus 2. As you can see, this curve is not intersecting x anywhere. That means I do not have any real solution, any real steady state for this system. So I can represent the effect of m, a parameter, on the possible steady state using this type of plot. There is a better way of representing the same thing. That's what I have drawn here, and this type of plot is called bifurcation diagram. What you do in bifurcation diagram, you take the parameter which is showing this type of effect, for example in this case m, on the horizontal axis, and the steady state values of x, the dependent variable, on the vertical axis, and you try to plot. So obviously when m is negative, m is less than 0, I have no real steady state, so nothing is shown in this region, When m is equal to 0, this is this position, I have only one steady state, so I have 1 point. And for m greater than 0, for all positive values, I have this quadratic form. So I have two solutions, plus square root of m minus square root of m. So I get two curves like this. So I can easily identify, suppose I have a positive value of m, then I will have two steady state. One here, the other one is here. This type of diagram where you take the parameter which is affecting the number of steady state in the horizontal axis and the steady state value. Remember, it is the steady state value of the dependent variable in the vertical axis, and then you plot the curves, and the curves represent the number of possible steady state. This type of curves are called, or plots are called, bifurcation diagram. And here I have the bifurcation diagram for the equation dx dt equal to m minus x square. Notice one thing, this line on the upper line is bold and filled, the lower line is dotted. I have used this dotted line to represent that this particular steady state, the steady state on all these, along this line, anything, anywhere, if you take any steady states, these are all unstable steady state. I will show how to calculate the stability of a steady state on a bifurcation diagram. For the time being, let us move into a different system. The example that I have given just now is for a single ODE. What will happen if I have more than one ODE? So let us take a system of ODE to understand the effect of a parameter on the behavior of the system. So I have a simple system of ODE, dx dt equal to m minus x square, the same equation that you have earlier, and then dy dt equal to minus y. So I have a system of ODE. So I want to see how the system's steady state get affected by m, the parameter. So effect of m will be seen on the steady state behavior of this system. So let us look into it. If m is less than 0, as we have discussed in the earlier case, as the equation is same, m minus x square, so obviously you do not have any possible real steady state for this system. Remember, to get a steady state for a system of ODE like this, both dx dt has to be equal to 0 and dy dt also has to be equal to 0. So both these two has to be equal to 0 at the steady state. So when m is less than 0, I have no real steady state. When m is 0, if I draw the phase portrait, I can see this type of graph shown here. These two are the null lines, and the intersection point is 0, 0, and that is my steady state. Let us look into trajectories. If I start somewhere here at t equal to 0, I follow this curve and collapse at the steady state. If I start somewhere here, I follow the arrows and collapse at the steady state. So the phase portraits are telling me if I start from these right hand quadrants, I move and collapse at the steady state. What happened on the left hand quadrants? If I start somewhere here, the phase portrait arrows are telling me that I will move along this path and I will diverge away from the steady state. The same thing is here. If I start from here, I will move along these and move away. So you can see from one side, the left hand quadrants, the system, the steady state is unstable. If you slightly get perturbed, then you move away from the steady state. On the other hand, on the other side, you are converging there. So it is like combination of two things. From this side, the right hand side, it is like a source node. On the other hand, this side you have, on the left hand side, you have the saddle type behavior. So I have a saddle node type behavior. Now let us take the third case. When m is greater than 0. When m is greater than 0, I have two solutions for steady states. I have two steady states. One is minus square root of m and 0, and the other one is plus square root of m and 0. I have drawn the phase portrait for this situation where m is greater than 0, and I have taken value m equal to 1 for this system and drawn the phase portrait. These colored lines are null lines. You can see the null lines have intersected at two positions. One here at this yellow dot, another one is this yellow dot. And as m equal to 1, you can see one intersection point is at equal to 1, the other one is at equal to minus 1. So look at the behavior of the steady state, or the trajectory, behavior of the trajectory around the steady state. If I start somewhere here at t equal to 0, I will follow this trajectory and eventually collapse at the steady state. If I start from this point at t equal to 0, I will follow this path and collapse at the steady state. If I start from this direction, again with time I will collapse at t equal at the steady state. The same is if I start from this direction also. So if I am at this particular steady state 1 0, I stay there. But if I slightly part up the system from there, I'll again collapse. The system will again collapse back to the same steady state. But that's not true for the other steady state, this one, minus 1 0. So here, if I am there at the minus 1 and 0, I will stay at that steady state. But if I disturb slightly, for example, if I bring at t equal to 0, the system is at this dot, and then with time, system will move away from the steady state. If I have the system here at t equal to 0, with time it will move away. If I start from somewhere here at t equal to 0, I will move towards the steady state and then diverge away. So the same thing here also. So you can easily recognize this particular steady state is nothing but saddle point. Whereas the other one, this one, is a stable node and sink. So in this example, you are observing two phenomena. When m is changed in different domains, when m is negative, you don't have any real steady state. When m equal to 0, you have only one steady state. When m is greater than 0, you have two steady state. So the number of steady state is changing with the value of the parameter. Not only that, in this case, the type of stability of the system is also changing. So here, when m equal to 0, I have a saddle node type which is unstable. Whereas, in case of m is greater than 0, I have two steady state. One is saddle point, which is obviously unstable, and the other one is a stable node type. So here, the parameter m is not only affecting the number of possible steady state, but also affecting the trajectories or the phase portrait of the system and the stability of these steady states. So let us now define this type of behavior. This type of behavior, where the qualitative behavior of the steady states are changing or getting affected by a particular parameter, is called bifurcation. And by qualitative behavior, what do I mean? By qualitative behavior, I mean that the number of possible steady states and the stability or the phase portraits around the steady states. So there can be a parameter which controls either the number of steady state, possible steady state, or it may control the stability of the steady state without changing the number, or it may affect both of them together simultaneously. So in all these cases, I will say this parameter causes bifurcation in the system, and the system has a bifurcation, and the parameter that is causing is this bifurcation will be called bifurcation parameter. So I can have a generalized broad definition. If the variation of a parameter changes the qualitative behavior of the steady state, I will call the system has bifurcation. Now let us look into another example and analyze in detail to understand this concept of bifurcation. So let us take the old problem of fish tank, where we are growing fish in a tank, and at equal interval we take out some fish to sell in the market. So as the tank has a limited space and resources, I will use a logistic growth model with removal as a negative term. So x is the number of fish in the tank at any time. So the rate of change of number of fish is dx dt is equal to r into 1 minus x by k into x minus d, where k is the carrying capacity, r is the rate constant for growth, and d is the rate by which, constant rate by which we are removing the fish. So I want to see whether this system has bifurcation with respect to this parameter d or not. So to do that, I have to first identify the steady states of this system, and then I have to analyze how this parameter d affects those steady state, either in terms of number of possible steady state or in terms of the stability of the steady states. So to get a steady state, I have to put dx dt equal to 0. That's a simple one. So I can put dx dt equal to 0. That means r into 1 minus x by k into x minus d is equal to also 0. So I will take x and everything else on the other side. So I can multiply this and I get a quadratic form like this: rx minus rx square divided by k minus d is equal to 0. So if I rewrite it, multiply k with d, multiply k with rx, and then I get rx square minus krx plus kd equal to 0. Note that I have multiplied both sides with minus sign, so that now I have got positive sign here, rx square minus krx plus kd equal to 0. This is a simple algebraic rearrangement. So I have a quadratic equation for x. That means x will have at least two solutions. So x equal to kr plus minus root over square root of k square r square minus 4r kd divided by 2r. Is simple following the rules of quadratic solutions. So now I want to see how d will affect the value of x and the steady state obviously, and the stability of the steady states obviously. So let us look into it. So at steady state, I have calculated value of x is this term, and I want to change the value of d here to see how this x changes. Let us take at d case 1, which is where d is less than 0. Now is that possible? Actually in our case, d is representing the rate by which we are removing the fish from the tank. So d cannot be negative, it will be always positive or equal to 0. So let us take the case 2, d equal to 0. That means fishes are growing but we are not removing anything from the tank. So in that case I can put d equal to 0 in this equation, and I get this term x equal to kr plus minus square root of k square r square minus 4rk into 0 divided by 2r. I can simplify it. So this whole thing becomes 0. I get kr plus minus square root of k square r square divided by 2r. So square root of k square r square is nothing but kr. So I get this one here, and if I cancel r because r is not equal to 0, so I get k plus minus k divided by 2. So that means I have two steady state value. When I take the plus sign here in this equation, I get x equal to k. If I take the minus sign, then x equal to 0. So that means when d is equal to 0, I have two steady state for x. One is k, another one is 0. So let us look into the third case. we have discussed two cases. One, d is negative, which is not possible. One is d is equal to 0, where I have two steady state k equal to 0. I take the third case where d is greater than 0. So here d is greater than 0. Look into the solution for x. This is this quadratic solution that we have got. If d is greater than 0, then we may have a trouble. I have k square r square minus 4 r kd in the square root. I have to keep this whole term under square root as a positive thing, because otherwise I will not have any real solution. So if I have to keep k square r square minus 4 r kd, which is under the square root, as a positive valued thing, that means this whole thing 4r kd has to be smaller than k square r square, otherwise I will get a negative value there. So that means to get a real solution, I have to keep k square r square, this is here, greater than 4r kd, greater than 4r kd, so that k square r square minus 4r kd is a positive thing. So this will give me that k square r square minus 4r kd is greater than 0 or greater equal to 0. I cannot have a negative value there, otherwise I will not get a real solution. So if I rearrange this inequality, then what we get is that d is less equal to kr4. I have cancelled one r because r is not equal to 0. I have cancelled one k because k is not equal to 0. So d is less equal to kr by 4. This inequality has to be satisfied so that I get this relation. And then I will have a real solution for this system. So let us consider the case first where d is equal to kr by 4. So if d is equal to kr by 4, so I am taking the value of d here, kr by 4, then I have only one steady state value. I can easily calculate k square r square minus 4r kd. So kd is replaced by kr by 4. 4 and 4 get cancelled, so I get k square r square minus k square r square, which is equal to 0. That means x equal to kr plus minus square root of 0 divided by 2r, which is equal to nothing but k by 2. So when d is equal to kr by 4, I have one steady state, and that is equal to k by 2. What if d is less than kr by 4? So in that case, what will happen? This whole thing, as I replace the value of d with a value which is less than kr by 4, this whole thing in this bracket will be less than k square r square. So that means I will have these two solutions. X equal to kr plus, I have taken the plus sign from here, square root of k square r square minus 4r kd by 2r, and then another solution with this negative sign, kr minus square root of k square r square minus 4r kd by 2r. So when I have d equal to kr by 4, I have only one steady state at k by 2. When d is less than kr by 4, I have two solutions. One is this one, the other one is this one. So I have two steady states. So let us pull all this together and represent it graphically. So what I have, this is my ODE. My generalized solution for the steady state is from the quadratic equation is this quadratic solution. So I have plotted a bifurcation diagram here. D is the parameter with respect to which I am studying the bifurcation. So D is in the horizontal axis, and the x is the dependent variable, and the steady state value of x is here. Remember, this is the steady state value of x. So when d is negative, that means in this direction, d is less than 0. That is not possible because d has to be positive or equal to 0 in our system. So I have nothing on this side. When d is equal to 0, I have two steady state. X equal to 0, other one is x equal to k, that we have discussed just now. When d equal to kr by 4, and what I have done here, I have taken r equal to 1 and I have taken k equal to 100. So kr by 4 is nothing but 25. So when d is equal to 25 or kr by 4, I have only one solution. If you remember, just in the previous slide we have derived that. So that solution is k by 2. That is k by 2 is equal to 50 in this case. But in between this, d equal to 0 and d equal to kr by 4, d is positive but lesser than kr by 4. So in that case, I have two solutions, if you remember, from this quadratic relation. One with this plus sign, another one is with this negative sign. So if I take, for example, 20, so I have one solution here, the other solution is here. So let us explore this bifurcation diagram further. If you remember, in the first bifurcation diagram that I have drawn for dx dt equal to m minus x square, I have one solid line and the other line was dotted, and I said that that dotted line represents unstable steady state. Now the question is, how do I calculate stability of steady states in a bifurcation plot? So the same thing we will do here. We will try to understand the stability of the steady states shown in this bifurcation diagram. I have a curve here, which is a parabolic curve, which represents the steady state, possible steady states when d is varied from smoothly from 0 to kr by 4. Remember, when d is negative, I don't have anything real because d cannot be negative in this case. When it is bigger than kr by 4, I have no solutions, real solution. In between 0 and kr by 4, I have this parabolic curve representing that I have two possible steady state. And I want to see the stability, or I want to calculate the stability of these possible steady states. So let us take d equal to 10. If d equal to 10, then I have one steady state here by this red dot, and I have another steady state here by these green dots. And if you do the calculation using this relationship, you will get, I have already done that, x equal to 88.73, this one is 88.73, and the other solution is 11.27, this is this one. So now the question is, these red dot and green dot, which are representing the steady states when d equal to 10, are they stable or unstable? So let us do the calculation for that. Let us take first the case where the steady state is at 11.27. And if you remember, for one-dimensional system, when we were discussing about the direction field, we have used a tabular method to calculate the steady states. So we will use the same thing here because I have just one ODE. So let us make the table. I have drawn the table. If you remember, table should have 4 columns: x, the derivative, the sign of the derivative, and the arrow. And I have 3 rows. In the middle row, I have put the steady state value, that is the 11.27 here. And I take a slightly bigger value on the upper row, that is 12 I have taken, and slightly lower value than the steady state, 10 in the lower row. For 11.27, obviously the dx dt is equal to 0, you can calculate it. So the arrow is here horizontal. Whereas if I take x slightly lesser, 10, then dx dt is minus 1. You can put the value of x equal to 0, x equal to 10 in this ODE with value of r equal to 1, k equal to 100, and d equal to 10, you will get dx dt is equal to minus 1. So the sign of the dx dt is derivative is negative. That means my arrow will be pointing down. I have taken the slightly higher value, 12. Again, using the same ODE, I put the value of x there as 12 and take r equal to 1, k equal to 100, d equal to 10. I get 0.56 and the sign is positive. That means the arrow will be pointing towards this. So what I can do, I can put the arrows on this red dot based on this result that I have got in a tabular fashion. So that's what I have done. So as you can notice, this red dot is a steady state, that is 11.27 when d equal to 10. So x will stay there if you don't perturb it. But if you perturb it slightly, it will move away. One arrow is pointing up, one arrow is pointing down. So that means this point is unstable. You can do this calculation for any point for value greater than d from starting from this value of d up to value less than kr by 4, so that along this whole curve, you will see this whole curve, all points on this whole curve will give steady states which are unstable. Let us look into the green dot, that is 88.73. Again, I will use the tabular calculation. So I have a table with 4 columns and 3 rows. The middle row is representing steady state 88.73. Obviously, the dxdt will be 0, so I have a horizontal arrow. I took a slightly higher value, 90 here, and I put the value of 90 in this x, in this ODE, and k equal to 100, r equal to 1 as I have mentioned here, and d as we have decided is 10. So if you put those values, plug together and calculate dxdt, you will get minus 1. So I have a negative sign. That means the arrow is pointing towards the steady state, the horizontal one. If I take a smaller value of x, say 85, then if I calculate dxdt using the same relationship, we get 2.75. It's positive. That means arrow will be pointing up. So if I put the arrows, I get like this. So both the arrows are pointing towards the steady state at 88.73. That means if x is at 88.73, it will stay there. But if you perturb x slightly, then from higher value, it will again collapse at that 88.73. From lower value of that, again it will, with time, it will collapse there. So this point is stable. You can try any other point along this curve up to this. You will see all points are stable steady state. So this upper curve is a stable steady state, whereas this lower one are unstable steady state. So let us compile all these in one single bifurcation plot. The ODE is given this one for my fish tank problem. The solution, generalized solution for steady state is given by this relation, and I have drawn the bifurcation diagram here for specific value of r, k, and I have taken d, which is causing the bifurcation in the horizontal axis, and the steady state value of x in the vertical axis. And when d is negative, that is not possible because d has to be positive in our case, because that is the rate of removal of the fishes, it cannot be negative. If d is equal to 0, I have two steady state, one here, one here. The curve is intersecting only at 2 points. If d is bigger than kr by 4, then I do not have any real solution, so you don't see anything on this side. If d is equal to kr by 4, then I have only one possible steady state here, which is k by 2. In between, from 0 to kr by 4, I have two possible steady state for each value of d as shown by these smooth curves, and this upper curve, upper steady states are all stable steady state, and the lower steady state, these in the steady state in the lower curve are all unstable steady state, and that's why the lower curve is shown as a dotted line. So what I have discussed till now, I have taken a ODE and I have identified the steady state, and then I have picked one parameter and I have taken different cases of that parameter and again calculated number of possible steady state. So that told me whether the number of possible steady state in this system is getting affected by the parameter. In this case, the parameter is d, and that is true. Based on d value of d, number of possible steady states are changing. At the same time, I have also shown you how to calculate the stability of each of the steady states. Now, we have seen bifurcation, but let us now look into, for this particular example, how this bifurcation will actually affect the dynamics of the system. So we know I can have two interesting regimes when d is equal to, when d is in between, suppose 0 and kr by 4. If I take r equal to 1, k equal to 100, then kr by 4 is 25. So let us first take a value of d when d is less than kr by 4 or greater than 0. I have taken d equal to 20 and I have drawn a direction field plot here with t in the horizontal axis, x in the vertical axis. So if you see the bifurcation plot here, D is here at 20, so that means I will have one steady state here, another steady state here. So bifurcation plot is telling me that I should have two steady state, and one is unstable, this one is unstable, other one is stable. So in the direction field also, I have one steady state here near at 30 and another steady state near 70. So if I start at this steady state, if I start somewhere here at t equal to 0, I will remain in this steady state. If I start at this steady state, I will stay at this steady state. So if you start with 70 fish, then you will always remain at 70 fish in that tank. If you start at that 30 value at the steady state, that is the number of fishes at the very beginning, then you will stay at the steady state. But if you start growing your fishes with a value in between these two steady states, say x equal to 40 here. So you are starting with your fish tank with 40 fishes. When r equal to 1, k equal to 100 and d equal to 20, that means you take out 20 fish per unit time, then the direction field is telling that I will follow these arrows and will eventually collapse at this steady state, which is at near 70. If I start at t equal to 0 with 90 fish, my direction field is telling me I will follow this trajectory and collapse at this steady state. So this is a stable steady state. Whereas if I start with a number of fish below this unstable steady state, this is the 30, then what will happen? For example, if I start with 20 fishes, then I will move in this direction away from the steady state, and as my fishes get used up by picking up, I will eventually go towards 0 fishes. So this one is unstable. What if I take a different value of d? Now I have taken a value of d as this kr by 4, that is 25. Remember, r equal to 1, k equal to 100, so kr by 4 is 25. I have taken d having a value equal to 25. That means I am removing 25 fish per unit time from the tank. So my bifurcation diagram is saying that I will have only one steady state here. So if I draw the direction field here with t in the horizontal axis, x in the vertical axis, so here I have the steady state. The direction field is telling this is the steady state, and obviously the bifurcation plot also tells me the steady state will be at k by 2, so that is 50. So if I start with 50 fishes at the beginning at t equal to 0, I will stay at that steady state. I will always have 50 fish in my tank. If I start with slightly higher value, that means I am starting with a number of fish bigger than 50, the steady state value, say 60, then my trajectory in the direction field is saying that with time that will decrease and eventually I will reach 50, the steady state, and then with time it will be stable there. But what if I start with a number of fish slightly lesser than 50, say 40. So at t equal to 0, I have only 40 fish in the tank. And I am removing, they are growing by logistic growth, and I am removing 25 fish per unit time. So then my direction field tells me that this will be the path followed by x. So number of fish will eventually decrease. It will move away from the stable steady state, the steady state at 50. So as you can see, from one direction this is stable, from the other direction it is unstable. So this is semi-stable. So this example explains how the bifurcation plot in combination with the direction field tells me how a particular parameter affects the steady states, possible steady state, and the dynamics around the steady state for a particular system. So let us jot down what we have learned in this video. The key points are: change in value of a parameter may affect number of possible steady state in the system. It can affect the stability of the steady state, or it can affect both number and stability. And such changes are actually changes in the qualitative behavior of the system. So when such changes occur, when such qualitative behavior change occur due to change in the parameter value, we have bifurcation in the system. And the parameter which is causing these such changes is called bifurcation parameter. We have discussed how to draw bifurcation diagram. So bifurcation diagram shows us the effect of bifurcation parameter on number of possible steady state and the stability of those steady state. Thank you for watching. We'll discuss further on this topic in the next video.